you everybody who is watching this video? I'm very happy to have you today. My name is Sir Olenjolai Moko TAYAI Losingo. Just simply call me Sir Olenjolai from Tanzania, beautiful country, eastern of the African continent. I'm very happy to have you, whether you are a national or international viewer. When I say national viewer, that you're Tanzanian, or you are international viewer from any of the continent, from any country across the world. I have a good news today concerning about our online institutions, and I would like to take this opportunity to welcome you right now officially into our online institution that called Online Undergraduate Polytechnic Institute of Tanzania in square bracket OLENJOLAIM. Simultaneously, because I'm teaching mathematics, I'd like to welcome you into one of our YouTube channels. We have 2 institutions and 4 online schools, and we have also 6 YouTube channels. One of them is called Online Undergrad Polyinstitute of Tanzania in square bracket OLENJOLAIM. Well, what are we doing? What the vision that we have in Online Undergraduate Polytechnic Institute of Tanzania? That the good questions. Well, we have an assignment that we have to teach, train, incubate, mentor, leads, and even encourage some groups of some undergraduate students in Tanzania and even international students will be ready to extract knowledge from the classroom instructions in mathematics and science subjects, to combine science subjects and even engineering subjects, to combine the knowledge which extracted formally or informally with the knowledge extracted from the Word of God written in the Holy Bible, and combine these 2 knowledge in order to solve real-life problems. So simply, in a simple sentence, we have just one sentence which defines the vision that is written in your mind that we like to write onto every students of ours. These are our visions. We have an assignment to teach, to train, to incubate, mentor, leads, and even encourage some students who will be ready to extract the knowledge from the informal and the formal education, to combine with the knowledge extracted from the Holy Bible, or from the word the knowledge of the Word of God from the Holy Bible, and in order to solve real life problems. So it has 4 parts. Number 1, to extract the knowledge from the formal or informal classroom instruction. Number 2, to extract knowledge from the Word of God written in the Holy Bible. And the 3rd part, to combine these 2 knowledges. And the 4th part, now to find a particular problems that need these combinations of these 2 knowledges. I'm a product of what am I telling you. I've been doing this business for more than 7 years right now, and I've been successful, and I thank God for His success, because it was indeed by my own power. Warning: when I'm teaching you about higher engineering and scientific mathematics, it doesn't mean that Olenjolai knows everything about higher engineering and scientific mathematics. I just know small portions of it. But what I know, I'm ready to teach others. It's my assignment. It's my responsibility to teach others what I know. I'm still learning every day about higher engineering and scientific mathematics. So our main goal here is to see our continuing and even our graduate students who will be able and capable, who will be solving real life problems. So one of our specific objectives will be helping you to do well in your testing, in your continuing assessment, and even in your final exam. We'll be helping you throughout the process, because we want to reduce any kinds of disgrace before you that will encounter you along your way of success. We have so many departments in this online institution. But one of the departments that we have in the Online Undergraduate Polytechnic Institute of Tanzania in square bracket OLENJOLAIM is called the High Engineering and Scientific Mathematics. And there we are teaching you formally, we are teaching you 12 modules or 12 courses. And today we have 1 course there written on the blackboard. And these 12 courses we are focusing the curriculums of the Tanzania Commissions for Universities and curriculums of National Technical Council for the Technical Education, that's called NACTE. So the module or the course that we have today is called Differential Equation and Complex Variables, and we are in chapter 3. We are done with chapter 2, which was actual that finding ordinary and singular point of ordinary differential equation. So we are in the 3rd chapter, and this is titled as power series solutions of ordinary differential question near the here ordinary point. And this is lecture 8. I'm going to introduce you today existence theorem, and even lecture 9 will be covering the same chapter, lecture 10, lecture 11 possibly, and even lecture 12 if I'm not mistaken. So this course at Dar es Salaam Institute of Technology is being studied as a second year course in the first semester. So I believe that you have so many information right now, and I would like just to do the quick review before I begin the new concept before you. So the quick review of previous lecture, we've been discussing that the standard differential equation is P of x double dash then plus Q of x, because we are going to record this equation throughout the entire branch of mathematics. Then we have R of x y is equal to 0. So we say that if P of x is equal to x naught is equal to 0, this is not equal to 0, then we used to say that x naught is ordinary point. Ordinary point. Again, we say that if P of x is equal to x naught, but it's not necessary to be 0, this is equal to 0, then we used to say that then x naught is the singular point. So we are going to use these two knowledges for the rest of the topics right now. So again, another point that we have existence theorem. We have existence theorem. Say existence theorem. So simply say that the existence theorem, before even we state it, existence theorem is a theorem. It's a theorem that is used to solve problems of ordinary differential equation near the here ordinary point. Near the here ordinary point. So this is the applications of existence theorem before even you know what is it. So now let us state the existence theorem, and this is stated like this one, that is say if x is equal to x naught, if x is equal to x naught is an ordinary point, is an ordinary. So given that is if x is equal to x naught is an ordinary point of the differential equation, is an ordinary point of differential equation. Differential equation P of x y double dash plus Q of x y single dash plus R of x y is equal to 0. Then we say that then the general solution of ordinary differential equation above is given as this, that y is equal to summation from n is equal to 1 to infinity of what? Of a subscript of n, then we have x minus x naught power n. So simply, just let me write existence theorem of ordinary differential equation is given as this. We have y is equal to the sigma notation from n is equal to 1 to infinity. Then you have a subscript of n, then you have x minus x naught power n, and this is equal to a of x, a y1 of x plus b is the constant, arbitrary constant, y2 of x. So this is what we call existence theorem. However, that these are the two formats, even this format is enough, but we'll be expressing our solution in this format. Okay? So y is the solutions of ordinary differential equation which have coefficient which are variable coefficients. That's what we call them, which are variable coefficients. So we say that also to simplify, or for simplicity, to simplify the concept, we say that let x not to be equal to 0. So let x not is equal to 0, then we say y is equal to summation of n is equal to 1 to infinity, and then we have what? A subscript of n, then x for n. So this is the format of what? And we can express this one into a by 1 of x plus b y2 of x. So this is the simplified existence theorem. So we say that where a and b are the arbitrary constants, and y1 and y2 are the linear independence power series solutions, which are analytically at the point x is equal to x naught. So, and this will be only equal at x is equal to x naught is equal to 0. Okay? So today we have a very interesting business in this chapter. We're going to solve a question, and then I will show you today the format of the power series solution. So you have to stay tuned. So let me define. We said that whereby A and B in that formula are arbitrary constants. Arbitrary constants. A and B are the arbitrary constants. Again, we say that y1 of x and y2 of x are linear independent, linear independent power series. So these are the independent power series, and we will see them soon. Linear independent power series. Linear independent power series solutions which are analytically at the ordinary point, which are analytically at ordinary point x is equal to x naught. X is equal to x naught. So in order for us to solve ordinary differential equation by using existence theorem, we need first of all existence theorem from the beginning, but later on, in the midst of our solution, we need again another theorem which called the identity theorem. So this is the first theorem. So ladies and gentlemen, let me now teach you about another theorem which you need it. And it's rarely seen actually that it will be seen for the careful mathematicians, but for the mathematicians who will not be careful, they cannot notice it. So we call it identity property or identity theorem. So we'll need this theorem also later on. And need from this lecture 8, we'll need it in lecture for the rest of the lectures until the end, before the applications of or differential equation. So we say that this identity theorem, we say if we have sigma notation from n is equal to 1 to infinity. Here we have a subscriptive of n, and then we have x minus x naught, for instance, power n. Is it? Yeah. So, and then this one, for instance, in another scenario, is equal to n is equal to 1 to infinity. Then here it is bn. Then this is x minus x naught n. Okay? So if that's the case, we say that actually in mathematics you're allowed to say so. We say that then it is the case, we say a subscript of n, the coefficient, will be equal to b subscript of n. So that's the theorem. So this is the theorem. But you'll need it later on. What happened here? The sigma notation is the same, so it will cancel. X minus x naught to power n and x minus x naught power n is the same, so we can cancel. So finally remains with coefficient of a subscript of n, which will be equal to b subscript of n. That's all. That's all. Okay. So after having those two theorems now, we have existence theorem, we have identity theorem. Then now we are well equipped as undergraduate student to solve the first simple ordinary differential equation and have power series solution of that ordinary differential equation. Are you ready for that? Are you ready? Are you ready to enjoy the beauty of higher engineering and scientific mathematics? Are you ready to solve the ordinary differential equation by using the existence theorem and identity theorem? If you are ready, join me right now into this interesting business. So this is example 23. We ended in previous chapter. We ended example 22 where I left it to example 21 and example 22 as the homework. So example 23, this is not actually that a concept because we'll be solving even tough example. This is the fundamental. I'm always beginning from the foundation. So I always solve simple examples and then I go to the moderate examples and hence I solve complex examples. Okay? Find a series solution in powers. Okay, in powers of x. Okay, of x of ordinary differential below. In some of the book, you just find a question that solve or find a power series solution. That's all of the differential equation below. Y is equal to 0. Okay, so that is our first example of chapter 3, which is titled as power series solution of ordinary differential equation near the ordinary point. So find a series solution or find a power series solution in powers of x, so of ordinary differential equation below. So here I forgot equation below. So this is the ordinary differential equation. So solution. Okay, solution. So this one we can express it. So first of all, the first state, we say that we can rewrite, or we can have our differential equation that this is second derivative of y with respect to x plus y is equal to 0. Or in other words, you can write that y double dash plus y is equal to 0. So these are the same notation as I taught you in previous chapters. Okay, so afterward, the next state now we go the second state. First of all, we don't know that we have to solve this differential equation near to its ordinary point or near to its singular point. So the first state, the second step, we say that check if x naught is ordinary point. So how do we do that? You have to refer chapter 2. I've taught you, and in case you forgot, how can you find the ordinary point or check if there is the ordinary point in the differential equation, then refer lecture 7, ordinary point, refer lecture 5. Because 6 and 7 is regular and irregular, singular point. Refer lecture 5, lecture 4, possibly, lecture 4. Okay, so how we can check? First of all, we have to remember the standard differential equation, which is p of x double dash plus q of x y single dash plus r of x y is equal to 0. So you have to compare it with what? With the standard given equation. So p of x is equal to 1, q of x for that case is equal to 0, and then r of x is equal to 1. So then we remember the condition for a point to be ordinary point. We say that if p of x is equal to x naught is equal to 0, is not equal to 0, then we say that x naught is ordinary point. Interesting. So this is the ordinary point. So then p of x is 1. So because p of x is 1, so when we find p of x is equal to x naught is equal to 0, let's say, okay, this one is equal to 1. So 1 is not equal to 0. Therefore, then x naught for this point, it means x naught of this differential equation is ordinary point. So it's an ordinary point. So now we can find a power series solution near the ordinary point, because the question didn't state. You see the confusion. The question didn't state whether that we have, because we can solve this differential equation near to its ordinary point or near to its singular point if it is there. So this is the second state, ladies and gentlemen. When we go for the third state. The third state now, we say that we call existence theorem. We call existence theorem that I taught you a few minutes ago. So existence theorem states that y is equal to sigma notation from n is equal to 1 to infinity. Then we have an, then we have x power n. Okay. So then we have to form all the three. We have one, we call it differential coefficient. So let me form other two differential coefficients, and we have to be careful because you have to avoid having or eliminating the differential coefficient in the given differential equation. So we have this y, this is non-differential coefficient. When n is equal to 1 to infinity, then you have an x power n. So where we have y like this point, we are going to substitute with this expression, right, in sigma notation. So then let us differentiate. Let us find y single dash. Y single dash is equal to first derivative in this sigma form. So we don't do anything else right now. Just let us keep on infinity n is equal to 1 on the sigma notation. We cannot do anything else with a subscript of n, but we have to do something by using the power series, by using the power formula. We'll have n and x power n minus 1. Right? So we go, let me teach you slowly. So y single dash, then we have here n is equal to 1 to infinity. Then simply this will become n as coefficient, a subscript of n, then you have x power n minus 1. So listen careful. Listen careful. I ask you, please stop writing. Listen first, and then you'll pause the video and you write everything. Write in steps, please, because I can leave you, and even you can fail to understand this concept while it is very simple concept for engineers. So in this case, if we leave this first order differential coefficient this format, then we will be eliminated, because when you substitute n is equal to 1 here it will be 1, here it will be a1, here it will be x power 1 minus 1, 1 minus 1 is 0. So because it is 0, x power 0 is 1. So it's going to eliminate and fade out all of this expression. So what we have to do as engineers, we have to raise this first counting index by 1. We just raise only this because we want to avoid having 0. Y dash is equal to 0, or y dash is equal to, it means that we are avoiding y dash term to miss the x term. So in this case now 1 plus 1, when we'll be starting from n is equal to 2, so then our first term will be containing x power 1. Right? It's similar at this point. We cannot say that the n is equal to 0. Because when we say n is equal to 0, x power 0 is 0. So the first term is going to fade out, which is not allowed in differential equation. So simply now, y single dash, it will be the summation or the sigma, n is equal to 2 to infinity, hence n a subscript of n x power n minus 1. Okay? So suppose that this is equation 1. Okay? And suppose that this is equation 2. And then suppose that this is equation 3. Have to be careful. And suppose that this is equation 4. So then we are going to differentiate to find the second derivative. To find the second derivative, we have to differentiate the first derivative. So this will be y double dash. So then we don't touch at this time the first counting index, because the last counting index is always infinite. So here we are going to have n, a, n. Hence again, we have some changes here. This will become, by using power series, n minus 1. And then here we have x power n minus 1 minus 1. Right? So then these expressions will be y double dash. So then we still have n is equal to 2. And here we have infinity. Okay? N is equal to 2. Excuse me. This existence formula starts from n is equal to 0. Excuse me. N is equal to 0. Is this it? Let me check. Yeah, n is equal to 0. So even if I made some mistakes before or earlier, then correct. The first counting index is n is equal to 0. So even here, we have n is equal to 0. Thank God to remind me that. Even here we have n is equal to 0. And even here we have n is equal to 0. So if we have n is equal to 0, 0 minus 1, we have x power negative 1, which is not allowed. So then, again, we have 0 plus 1 is n is equal to 1. So at least the first term, if we substitute n is equal to 1, a 1, so we start with the term which have x power 0, but the second term will be x power 1. The third terms will be x power 2, etc. So even here that we have this time we have n is equal to 1. So even here we have n is equal to 1. So then we have n times n minus 1, then we have a sub n, then x e power n minus 2. Again here, if you substitute n is equal to 1, we'll have x e power negative 1, which is not allowed. It's not allowed in mathematics, and especially that when we are dealing with power series solution. So you know what happens? So we say that we have y double dash is equal to sigma notation from n is equal to 1 to infinity. As we say, n times n minus 1, a sub n x power n minus 2. Okay? So it means that we have to raise the first counting index by 1, but we don't lower the summation index. Okay? To avoid that situations that I told you. So y double dash, this will be equal to sigma n is equal to 2 to infinity. Here you have n minus 1, a sub n x power n minus 2. We don't touch the summation index. So this one will be our equation 5. Alright? Equation 5. So then that was the third step. Let us go to the fourth step. We are going to follow 9 steps of solving this equation. It's a simple differential question. The first step, we say that substitute equation 4, equation 3, and the equation 5 in equation 1. Okay? What was equation 1? Equation 1 was y double dash plus y is equal to 0. So what is y double dash? So y double dash, we have this. It is n is equal to 2 to infinity. Then you have n times n minus 1. Then a subscript of n, then x power n minus 2. Then plus y. Plus y, it is sigma n is equal to 0 to infinity. A subscript of n, x power n is equal to 0. Okay, so you can formulate equation 6 possible. So suppose that this is equation 6. Okay, so we have equation 6, but this we call the generic terms. X power n and x power n minus 2, we call it the generic term. So we go for the fifth step. Have to keep on simplifying before we apply identity property or theorem. So the fifth step, we say that express both terms, because we have only 2 terms, both terms in the same generic term, the same generic form. And this generic form is x power n. So here you have x power n minus 2 in the first term. You have to eliminate. So how can we achieve that? So how can we achieve that? So we have the first term here, which is n is equal to 2 to infinity. We have n times n minus 1, a subscript of n, x n minus 2. So in order to express it, So we need to express this term in x power n. So we say that we have to raise summation index. I'm writing for you to remember by what? By 2 and the lower, simultaneously lower counting index. Counting index by the same factor by 2. So what will happen? So we have a summation n is equal to 2 minus 2, and here we have infinity minus 2. We have n plus 2, because we are breaking the summation index, n minus 1 plus 2. Then you have a n plus 2, and then we have x power n minus 2 plus 2. So then this term will be sigma notation, n is equal to 0 to infinity, and then we say that n plus 2, and here we have n plus 1, we have a n plus 2, and then there we have x power n. So we have achieved our main objective to express the first term in its generic form. So let us restore our first term in its position. So it was sigma notation, n is equal to 0 to infinity, and then here we have n plus 1 times n plus 2, a n plus 2, then we have x power n plus sigma notation, n is equal to 0 to infinity, and then we have what? We have a subscript of n, x power n is equal to 0. So this now we can formulate equation 7. Called equation 7. Then check the counting index of each term. This is the first term, second term. Check the counting index. Find that the counting index in both terms, they have the same counting index, which n is equal to 0, which actually that is simplified your work, because in case you find the counting index of either 2 terms or 3 terms or 4 terms or 5 terms is not the same, you have to make sure that you simplify them and equate all the first counting index. So from this state now we can jump into the next state. In the next state, we say that we go for the 6th state. So the 6th state, we say that check the common terms, okay? So we say that simplify, keep on simplify equation 7. How we simplify it? First of all, this sigma notation now is common for both terms. From n is equal to 0 to infinity, then we open bracket. Here we remain is n plus 1 as coefficient times n plus 2. Then we have a subscript of n plus 2, and then we have a subscript of n, and then we have x power n, which is common, is equal to 0. Okay? So if it is the case, we say fine, we are mathematicians and we love this subject so much. N is equal to 0, infinite, and then we have to check also the right hand side. So here we have n plus 1 times n plus 2. This is a n plus 2, and then we have a subscript of n, and here it is x power n, and this is sigma notation of n is equal to 0 to infinity. Then here we have 0 x power n. So what happens? So this will cancel with this. This is what we call the identity property. So the seventh state means that the seventh state we call identity property, right? Identity property. Identity property, I told you. So identity property, so this x power n and x power n will cancel. So now simply remains n plus 1 times n plus 2, a subscript of n plus 2 plus what? an, this is equal to 0. And this is equation 8. Very interesting equation in mathematics, because we are going to have a formula we call it generic, we call it the recurrence formula. Called the recurrence formula. So well, so we still continue with our business, our interesting business in higher engineering and scientific mathematics. And the business we have today, we are looking at the power series solution of ordinary differential equation near to its ordinary point. I believe that you enjoyed this beautiful song and beautiful chorus. So then we have this one. So you know what happens? We go for the 8th state. For the 8th state, we say that make, for this case, you have to check. We have a subscript of n plus 2 and a subscript of n. So in mathematics, we prefer to make this or to leave this term or this part of the term of the first, or this part of the term on the left side, and these parts which have smaller value of the subscript, we have to take them into the right hand side. So we say that make a subscript of n plus 2 the subject. Make it the subject. So to make it the subject, we say that we have n plus 1 on left hand side. We have n plus 2, a subscript of n plus 2. This is equal to negative a subscript of n. So to make the subject is just review of what you've learned or you've taught you during your form 2. So you have to divide by n plus 1 times n plus 2 on both sides, and divide here by n plus 1 times n plus 2. So simply this one and these terms will cancel. So you have a n plus 2. This is equal to what? Is equal to negative a n, or a subscript of n. Then you have n plus 1 and n plus 2. Wow, this is very important formula in mathematics. So you say that a n plus 2, this is equal to negative a subscript of n. And then here we have n plus 1. Here we have n plus 2. And then we say that this will be true when n is greater than or equal to 0. Why? What does this mean? Okay? What the meaning of this n greater than 0? We make decisions of the first term. Okay? The value of n for the first term will be defined by the last sigma notations after you have expressed the first count index of all the terms in the same value. So here it is n is equal to 0. So that's why that the conditions means n should be greater than or equal to 0 in order to get the terms there of the series as your power series solution. So this is very important to be in many power series solution, or in many cases when we solving problems, we'll be having this formula, and this formula has a special name in mathematics. We call it recurrence relations, recurrence or recursion formula. So the formula above is called the recurrence form. So it's called the recurrence form or recursion form. Very important, because especially in the testing, you'll be asked to find recursion or recursion. Recursion form. Recursion is recursion form. Okay, recursion form. So it can be recurrence form, called recurrence formula or recursion form. So in test 1 exam, in many cases according to my experience, because I studied this module or this course, and also I taught students, other students, for 5 years, and I've been helping them, and really they came to me when they are seeking the minimum marks for them to pass in the continuous assessment, but God was wonderful. They were ending on scoring A plus, not even the A, the normal A, it is A plus. So in many test exams, because of the time that you won't have enough time to solve for the entire power series solution, in many questions you'll be asked that solve up to recurrence formula. So if you'll be asked that to find a recurrence formula for the previous question, then you just end here, and then so you're waiting your 5 marks in exam. But otherwise, if you be asked that to find a power series solution, you have to continue the next other steps. Right? So then, so the next step now to find a power series solution, because remember that the general forms of power series solution should be a series, right? That means of power series. So series is the arrangement, or just it's a sequence. We call it a sequence, or yes, it's a sequence of the terms. First term plus second term plus third term, or first term minus second terms minus third term minus fourth term minus fifth terms, etc., and so on and so on and so on. Because for this case we have up to infinity. So this is infinite series that I told you at the beginning. So now, ladies and gentlemen, let me take you into the 9th step. Right? The 9th step, we say that find the value of A. The value of A for what? For n is equal to the first term, n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, let us n is equal to 5, etc., as well as you can. So what is our expression? We have an plus 2. This is equal to negative an. You have to be careful and listen and stop writing. Stop writing. It's the time now for solving. So let us begin with for n is equal to 0. So we have a 0 plus 2. This is equal to negative a with a subscript of 0. Then you have 0 plus 1. Then you have 0 plus 2. So then we say that in numerator we have negative a naught, and denominator we have 0 plus 1 is 1 times 2 it is 2. So 0 plus 2 it is 2. So our a2, whenever we find a2 in our general series, then we substitute with negative a naught over 2. Then we go for the next term when n is equal to 1. So when n is equal to 1, a naught will be 3. And then here we have negative a1. And then here we are going to have 2 times 3, right, in denominator. So simply this will make negative a1 over 6. Okay? So this one, later on, this we can express as negative a naught is the same if you say we have 2 factorial. Similarly, this one is the same if you say it is negative a1 over 3 factorial, because 3 factorial is equal to 6. Right? Okay, then we go for what? For n is equal to 2. So we are going to have a4, then we have negative a2 of what? Over, so we have now 2 plus 1, it is 3. Then 2 plus 2, it is 4. So simply this will make negative a2 over 5. Or over, okay, just we can end with what? 3 times 4. Or 4 times 3. But in previous steps, we found the value of what? Of A2. Found the value of A2. You're not limited. You can find maybe 3 terms. In case of exam, you can find maximum 3 terms are enough to give you the series. Okay? So you say that but you say that A4 is equal to negative A2 over 4 times 3. But A2, we found it is negative A0, better if you express over 2 factorial. So if that's the case, you say that A4, whenever we find A4, we are going to have negative 1 over 4 times 3, then times what? A2, which is negative, A0 over 2 factorial. Is this it? Yeah. Okay. So then, for this case, we say that this is equal to what? This is equal to positive A0, 4 times 3 times 2 times 1 factorial. This will be equal to 4 factorial, but it's positive today. Right? That is A4. So A4, it is positive. Then we say we can go for n is equal to 3. For n is equal to 3. N is equal to 3, we have A5, and this will make negative A3 of what? So we have 3, so 3 plus 1 is 4, and then 3 plus 2, it is 5. But what is A3? But we say A3 is equal to negative A1 over 3 factorial. This one. Okay? So we say that now A5, this is equal to what? It's equal to negative 1 over 5 times 4. Then we have A3. What's A3? It is negative A1 over 3 factorial. So negative A1 times negative 1, this will make positive A1. Then we have 5 times 4 times 3 factorial. It means that this is equal to 5 factorial. Just to simplify, because 3 factorial is 60 times 20, so it's 120. So even 5 factorial is 120. Then we can go for n is equal to 4. We can even end, how many times do we get there? We are going to have A0, A1, A2, A3, A4. But because this is the first example and it's the simplest, I would like to recommend you to find many terms as well as you can. So later, in case you find some of the terms are just disappearing, so are becoming zero, you know how you can navigate. Okay? So for n is equal to 4, we say that for n is equal to 4, for n is equal to 4, we say that it's going to be A6. This is equal to negative A4, right? A4 of what? Over 5 times 6. So then we find that A6, this is equal to what? Negative 1, 6 times 5, then A4. What's A4? A4, HC, A0 over 4 factorial. So this will make what? We make negative A0 over 60 factorial, 60 times 5 times 4 factorial. This is 60 factorial. You can end there, or you can go further and further and further as well as you can. But because we say, let us go for until n is equal to 5. So we are going to have A7. So A7 will be negative A5 over 60 times 7. Why? Because 5 plus 1 is 6, 5 plus 2 it is 7. So then so this will be negative 1 over 6 times 7. What is A5? A5 is A1 over 5 factorial. So simply, this is equal to what? Is equal to negative A1 over what? Over 7 factorial. So you can find other terms as well as you can, but those are enough because I know even now you are so exhausted. You say that, if this is the way that, if this is the all about power series solution, then I will solve other questions and skip this. No, can't skip it. According to the setting of exam, you have to know and you have to solve at least one power series solution question. We go for the 10th step. Don't worry about the number of steps. The issue is understand. You can pause the video and copy these coefficients or these terms that we have been finding, and then we continue on the 10th step. So the 10th step, we say that we call the recurrence formula. The recurrence, no, not the recurrence formula, excuse me. We call existence formula. We say that existence formula, this is y is equal to sigma from n is equal to 0 to infinity. Remember that you have to correct in case I made a mistake. And then we have a n x power n. This is going to be in power series. So let us define it. So if we define it, we find that y is equal to, so we have to be careful. When n is equal to 0, the first term is a naught, and then we have x naught. So we are writing, this is the power series, this is existence formula, but in shorthand form, in sigma notation. So right now we have to write the long series, the long series, the actual series, not in sigma notation. When n is equal to 1, we are going to have a1 and x equal 1. When n is equal to 2, we are going to have a2, then x squared. When n is equal to 3, we are going to have a3, then x power 3. When n is equal to 4, we are going to have a4, x equal 4. When n is equal to 5, we are going to have a5, x equal 5. When n is equal to, it's not common, so it depends on the series. When n is equal to 6, we are going to have a6 and then x power 6. And we ended it. When n is equal to 7, we are going to have a7, x power 7 plus dash, dash, dash. So the series is still continuing. Wow, we are about now to get the power series solution. Wow. So x power 0 it is 1, so we have y. Do we have a naught is equal to anything else? No. So a naught will be in our series, in our final series. Then we have anywhere else, we have a1. a1 is equal to anything? No, nowhere. The first value is a2. So we just leave, here we have a naught times x naught power 0, which is 1, plus what? a1 times x power 1. So we leave these first two terms because we don't know the value, right? So in case we know the a1 is equal to something, then we'll be remaining only a naught. So be careful with that concept because I know it has been confusing so many students. Then we go for the a2. The next term is a2. The third term, a2 x squared. So x squared will be there. We know the value of a2? Yes. The value of a2 we found here, it is negative a naught over 2. So it will be minus a naught over 2 minus a naught over 2. Short time, x come up with solution. We have the first term is a3. We know a3. We have an a3 it is negative. So may God bless you and this is 2 factorial. I meet you next time. Okay, just negative a1 over 3 factorial. Aha. So it is negative a1 over 3 factorial x cubic. The next term is a4 x power 4. x4. Next term is x4 x power 4. What is a4? a4, it is a naught over 4 factorial. So you just substitute. So remember that you can put even these terms in brackets. So a4, it is a naught over 4 factorial. And here we have x power 4 plus. Then the next term is a5 x power 5. Where is a5? a5 is a1 over 5 factorial. So it is a1 over 5 factorial x power 5. Then plus a6. Where is the a6? a6, it is negative a0. So it is negative a0 over 60 factorial x power 6 plus. Then we have a7. It is negative a1 over 7 factorial. So it is negative a1 over 7 factorial. Then x equals 7 plus dash, dash, dash. You know what the next step? You have to examine your series. That is what we call it in power series solution. So it's a solution of the differential equation, but in form of series. It's not in form of stories or a table, but in form of series. Okay? If you examine our series, first of all, we have on left hand side we have y. If you examine our series clearly as engineers and as mathematicians, we have a0, 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 we have a0. Then we have a1, we have a term which have a1, another term which have a1, another term which have a1. Aha! And then the rest are x is common, so we don't touch any, we don't touch our x. So let us collect it. So that will be the 11th step. 11th step, we say that collecting, okay, the like terms. The like terms, what does it mean? We have y is equal to a0 is common for some terms. a0 is common for the first term, second term, fifth term, seventh term. First, third, fifth, seventh term. So because it is common, so you can take it out and form its own series, because it will be, this is repeating periodically. It's a term that happens in the interval of one term. So you have a0. So if you take a0 out, here will remain with 1. Remain with 1. Then here we have minus x squared over 2 factorial. So minus x squared over 2 factorial. Then the next term is this one, which is positive. So it will be plus x power 4 over 4 factorial. Then minus x power 60 over 60 factorial. Right? This one. So then, because it is still continuing, we say plus dash, dash, dash. So we close that first part of the series. And then we say that plus a1. Again, we have a1 is common. It's common in the second term, fourth term, sixth term, eighth term. So you have a1. If we take it out, here remain with x. Then for the second term, for the first term, we remain with minus x cubic over 3 factorial. See now the interest solution. Then we have what? Then we have the system, which is a1. We took a1 out. It is x power 5 over 5 factorial. Then minus x power 7, the eighth term, over 7 factorial. This is still continuing to infinity, like that. And then we say that, therefore, this is our power series solution. power series solution in the simple form. So we used to end there, but however that lovers of mathematics, we can go further and express this expression in sigma notation like this, where we have sigma notations for this series and sigma notation for another series. So you have to think how those terms relate, and then you formulate an nth term, and then you use the sigma notation to present. But usual for many engineers and scientific students, we just end there. But for the lovers of mathematicians, we go further step from there. So that's the solutions of of the differential question which we have been given. Okay, so we'll be solving so many questions to find a power series solution near the ordinary point. So to find power series solutions of ordinary differential question near the ordinary point. So this is just the first example, the simplest example compared to other examples that we are going to solve. So this is the end of lecture 8. I thank God who have been with me in the preparations of this session, and I thank God who have been with you, and I thank God who have created me in his own image and likeness, and I thank God who have taught me this concept, and I thank God who have given me the great idea to teach national and international students, and I thank God who have given you opportunity to follow me and even to learn differential questions with me from the beginnings of sessions until now. And I thank God because I know that this idea and this knowledge will be helping thousands of undergraduate students in Tanzania and even worldwide. So I would like to invite you in the next session, which will be lecture 9. I will be solving, and I will be taking another differential question, and then I will be solving by using existence theorem. I will be finding the power series solution near its ordinary point. So I would like to remind you that to make sure that you subscribe into our YouTube channel. So click the buttons there, and then choose the options of all after you click the bell, so that you get notifications once we add a new video, because we are always adding at least one video in a day. So it means that we in online undergraduate Polytechnic Institute of Tanzania, square bracket OLENJOLAIM, we're expecting to have more than 500 high definition videos for training and for teaching high engineering and scientific mathematics. So make sure you subscribe, share this contents with your classmates, make sure to read descriptions in case you feel from your heart that you want to offer your free-willing thanksgiving to God for what you have received free of charge, because we could have charged you a lot of money. These are the worth materials actually that it was a deal, but God said that I have to offer him my free-willing thanksgiving for the gift, for the teaching gift, or for the gift of teaching that he has built in me. So this is why that I'm offering free, but there is high running cost for this program, and I'm not allowed to mention how much does it cost for a single video to from the preparations zone, then to the production zone, editing zones, and then the internet part, until that we just host them in the YouTube servers, and then finally we publish publicly to everybody, for everybody to enjoy worldwide. So it means that there are high running costs, but in case you feel from your heart that you want to support the high running cost, so that so many videos of high engineering and scientific mathematics to be online, so you can send your free-willing thanksgiving through this telephone number 0759745331, and the registered name is Olenjolai TAYAI. Again, in case you want to do the bank transactions, go to the descriptions below of this video. You will see that how you can send your free-willing thanksgiving through the bank account or bank account, and believe me that your free-willing thanksgivings will be respected with honor and to be used effectively and specifically for the running cost of this program. It won't be used otherwise else. So may God bless you. I'm always praying for you. I'm asking also to pray for me, especially that to carry on this great and even wonderful and hard work of teaching you step to step by using a simplified language, so that may God be with me and may God be with you during the learning and even during the pondering of this concept. So let us keep each other in prayer, because God is faithful and nothing is impossible before him. So may God bless you. I invite you in the next lecture, lecture 9. Don't miss it. And I'm ready to take you into the next level of thinking. And then always think that there is a particular problems in your community waiting you to solve as an engineer or a scientist. So don't make jokes, don't waste much time, gather the knowledge, and then go and try and find successful people. And then you'll find that